So one of the most important results of dealing with prime numbers is something called the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. And that's basically saying that you can take a number that's not 0, not plus or minus 1, you can break it up into primes. You can break it up into primes, which we call a product of primes. Now, there's several forms of the fundamental theorem of arithmetic, which some get really specific and give you a lot of useful information. But we're going to start off just with the general form, the most general form. This is sometimes called the number theory form. It says every integer n except 0 and plus or minus 1 is a product of primes. That includes primes themselves. So for example, if your number n were 3, notice 3 is a prime, then it would be a product of primes. It just has one prime in its product. If you had like the number 6, you could break it up into 2 times 3. You'd have a product of primes, you'd have 2 primes. If you had the number, let's say 20, that would be what, 2 squared times 5. That would be a product of primes. You have 2, 2, and 5. So even in case you just have one prime, like 3, that's still a product of primes. That's what we mean by a product. It's just a collection of primes. Okay, so this is a tricky one to prove. So let's start off by letting S, if I can get this to work, let S be a set, a collection of objects. So S is going to be the set of all integers n, where n is greater than 1 and n is not a product of primes. So imagine a set of all numbers that are bigger than 1, all integers that are bigger than 1, that are not a product of primes. So in reality, we know no such set equals. There is no such set, right? There is no such set. There is not such a set where a number is not a product of primes. Let's just pretend there is for the sake of argument. So we have this set, all its integers are bigger than 1, and all its integers are not a product of primes. So we're going to show this set is empty. We will show this set is actually empty. So I wouldn't know how to prove this, so if I wouldn't know how to prove this, I'd try maybe contradiction. So if I were to prove something's empty by contradiction, let's pretend it's not empty. So let's assume, to the contrary, that S is non-empty. What does that mean if a set is non-empty? That means there's something in it, right? Now remember, if you have a non-empty set of non-negative integers, and that's what we have here, right? The n's are not negative, right? They're greater than 1. So if you have a non-empty set, right? Non-empty set of non-negative integers, you have something called the well-ordering axiom. By the well-ordering axiom, that's in the very first section. S, this set, must have a smallest element, has a smallest element. I'm going to call that smallest element, what do I want to call it? M? Let's call it M. Okay, so this set S has a smallest element. So M is bigger than 1, and it's not a product of primes. So since M is not a product of primes, it's not prime itself. M is not prime. Now, we know M is bigger than 1 because it's in the set S. So M, which is bigger than 1, has to have positive divisors besides one in itself. Besides one or itself m, right? M is not prime, we're saying. M is not prime. It's bigger than 1, so it has positive divisors besides 1 or itself. Okay, so let A be a divisor of M. Let A divide M. And A has to be between 1 and M, right? Because it's a positive divisor other than 1 or M. So A has to be between 1 and M. Right, if you're a positive divisor of M, then you're less than or equal to M. You can't be 1, you can't be M, so you're strictly in between 1 and M. So, M is of the form A times B, right? With B, so B is also a divisor of A. B is a divisor of A, and B has to be between 1 and M as well. B can't be M, and B can't be 1. You can think that carefully through, but if B were 1, then that would be M is equal to A, which you can't have. And if B were M, then you would have A equal to 1, which you can't have. So B has to be between 1 and M. So B is an integer between 1 and M. Okay. Now, notice that A is not an element of S, and B is not an element of S. Why? Why is A not an element of S? Well, remember here, if I can get this to work, A is less than M, right? If A is smaller than the smallest element of S, then it wouldn't be able to be an element of S. So A cannot be an S. Also look at B, right? B is less than M, and M was the smallest element of S, so B cannot be smaller than the smallest element, so B cannot be an S as well. So A and B are not elements of S since A and B are less than the smallest element of S, which was M. Okay, so A is not an S. B is not an S. We know they're both bigger than 1, A and B. So that means A and B must be a product of primes, right? If they're not an S, then they must be a product of primes. So thus, A must be a product of primes. Let's say P1, P2, through PR. And B, since it's not an S, must also be a product of primes. Say Q1, Q2, QT, where each PI is a prime, and each QJ is a prime. So the PIs are primes and the QJs are primes. Okay, so now I'm going to go back to this equation here. I'm going to put it in red. This equation, A times B. And look at that. I'm going to substitute my primes, factorizations, for my A and my B. So thus, now let's say then, M is equal to instead of writing AB, I'm going to write P1, P2 through PR, Q1, Q2 through QT. And this shows that M is a product of primes, right? You got a bunch of primes multiplied together. But that contradicts the fact that M is not a product of primes, right? Remember, M was not a product of primes because it was an S. So let's say it like this. The fact that M is a product of primes, this contradicts the fact that M is an S. Right? M was the smallest element of S. So M was an S, so it's not a product of primes. So we have it's a product of primes and it's not a product of primes. So we got a contradiction. So how do we get the contradiction? By assuming to the contrary that S is non-empty. So therefore S must be empty. Therefore this set S is empty. So what does that mean if S is empty? This set is empty here. Well, that means there are no positive integers greater than 1 that are not product of primes. In other words, every integer greater than 1 is a product of primes. So hence, each integer n greater than 1 is a product of primes. Now, this only proves it for positive integers. Remember, we want to prove this for every integer besides 0, plus or minus 1. So we need to prove this for the negatives that are smaller than negative 1. So let's prove it for the negatives that are smaller than negative 1. So let's suppose you have an integer n that's smaller than negative 1. So we're doing it for the negatives below negative 1. That means you can rewrite n, your integer n, as minus k, with k greater than 1. Right? For example, if I have a negative number, negative 5 is my number n, then I could rewrite this as minus k, where k is 5. Right? And k, which is 5, is bigger than 1. Yeah, so if n is less than negative 1, I can write it as minus k, where k is greater than 1. Now, this k right here, oops, disappeared. This k that's greater than 1, we know every integer greater than 1 is a product of primes. So by the first part that we just did, by part 1 of what we've just done, k is a product of primes. Therefore, well, get this to right. Therefore, n equals minus k is also a product of primes. Yeah, so all you're doing, you're sticking a negative on the front of all those primes, and it's still a prime there. We have negative primes here. So that's it. We've proven it for the positive case that every integer greater than 1, this thing acts up, is a product of primes, and we also have proven it for integers less than negative 1 is a product of primes. So that's it. That's the proof. Go ahead and erase those. So that is the initial version, the easy version of the fundamental theorem of arithmetic to prove. The other versions are much more complex to prove, but more useful for actually working through problems. But this is the easier one to prove. It's still tough, but okay. So that's it for